Back to today's lesson. Today we are going to look at our topic, which is the topic of refraction of light. In particular, we shall be looking at refraction at plane surfaces, or what we call the flat surfaces, not the curved ones. And the plane surfaces, they include glass block, the prisms, water surfaces, and many others. My name, I still remain teacher Aheba William. I will be down to take you through this lesson. Let's dive into the work. Now, when we talk about refraction, what do we know about it? Remember, I know you have already looked at, or you might have already looked at the other topic, which is reflection, but this one is refraction. Now, when we say refraction, we are basically talking about the bending of light rays as it moves from one medium to another, which is of different optical density, or what we call different refractive index. Now, you may wonder, why does the light bend? The light bends simply because of one thing. I will compare it. I will give you a scenario. If you are tasked to run on a road, let's say whether it is a tarmac or it is a marram, they tell you to run. And then you also tasked to run in a bush. You run in a land which is full of bush with a lot of grass. If I ask you, which of the two, where you is likely to run in a straight line, you will tell me on the road, because you have less limitation. So similarly to light, as light moves from, let's say, one medium to another, it's like if you're running from the road, then you're entering the bush. Because there is bush, you'll be trying to avoid, let's say, colliding with trees. You're trying to avoid this and that. You'll end up not running in a straight line. So as light moves from one medium to another, its speed changes. If it was moving in a less dense medium, that is like when you're running on a clear road, you'll be running faster. But if it is running in a more dense medium, that's like when you're running in a bush, so you'll be running a bit slower, and this causes it to bend. So that bending is what we call refraction. So we see that the reason why refraction occurs, it's because light changes in its speed. And why does it change the speed? Because it is moving from one medium to another, which are of different optical densities. So let's look at an example of refraction. Like if we have our light ray, which is moving from, you see up here there is air, then it is entering glass. So it is moving from a less dense medium, which is air. It doesn't have a lot of material in it, entering glass, which is more dense. So it will bend. Now the bending depends. It may bend towards the normal or away. It may bend away from the normal. Now, when does it bend towards or away from the normal? If it is running, if it is entering, it is coming from air entering glass. Air is less dense than glass. So it will be bending towards the normal because the glass is more dense. But if it changed and it starts coming from this side, it is entering, it is moving from glass going to air, then it will be bending away from the normal because air is less dense, so it will be running away from the normal because it is now moving faster. So that is refraction and how it occurs, or what causes it. Let's look at some terms that are commonly used under refraction. Let's have our diagram here for reference. We have what we call the incident ray. Like you can see, this incident ray is AO, the ray which is falling or which is entering the boundary. That is the one we call incident. Like you hear the word incident, meaning it is falling, it is on coming in. So we call it the incident ray. Whereas the angle between that ray and the normal, I hope you understand what normal means from your mathematics. A normal is a line that meets a boundary at 90 degrees. That is what we call a normal line. So the angle between that normal line and the incident ray is what we call the angle of incidence. Then we have refracted ray, the ray meaning the ray which has been bent, the ray which is coming out. That is what we call the refracted ray, and here it is demonstrated as OB, from O to B, that is the refracted ray. And it is the angle between that refracted ray and the normal is what we call the angle of refraction. Then I had already talked about the normal line or the normal ray, that is the one which is entering. If it is a ray, if it meets the surface at 90 degrees, it will go through without bending. But if you can consider it an imaginary line, something like that, as long as it is meeting the boundary at 90, we call it a normal, either a normal ray, a normal line, anything like that. So like similar to reflection, refraction also has laws, and those laws, they don't have a specific order like we see Newton's laws. These laws they are just two. You can always start with any. The first one is similar to what we have in reflection, which says the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. I see sometimes students confuse this. They put here on. It is supposed to be in the same plane. And then the second law, which is the most important one in refraction, is for a given pair of media, the ratio of the sine of angle of incidence to the sine of angle of refraction is always constant. I'm going to explain this a bit more. It is the one that is known as Snell's law. In case you are asked to maybe talk about Snell's law, that is what we call the Snell's law. Now, what does this law mean? That if I have two media, let's say medium 1 is air, like we had already seen, medium 2 is glass. If I get sine in trigonometry, sine of angle of incidence, I divide it with sine of angle of refraction. For every given angle, the answer will remain the same. If when the angle of incidence is 30 and angle of refraction is 20, when I divide sine 30 with sine 20, the answer I get will be the same answer you'll get if the angle of incidence becomes 35 and the angle of refraction becomes 21. That's what this law means, that it will always remain that for as long as you have not changed the media. Okay? Now, this constant brings us to something else now. That the constant now we are talking about, that answer which does not change, is what we call the refractive index. Let's look again at our diagram. If I have air, the light is coming from air. It is entering glass. It is entering glass. The refractive index we are talking about will be if I am dividing the sine of angle I, dividing it to the sine of angle R. The answer I get will be the same when I get the refractive index for glass. I divide it with the refractive index of air. It's like I'm doing reverse. The sine in this being divided with the angle in this, sine of angle in this one, in medium 2. The answer I get will be the same as when I divide the refractive index of medium 2 with refractive index of medium 1. Now that is always simplified to make it simpler for you. You realize if we cross multiply here, N2 will go with sine R and 1 will go with sine I. So I always put it simple for my students that if you want to understand Snell's law in simpler terms, it just comes like this. That the refractive index multiplied with the sine in that medium. Since here air, if air is of refractive index N1 and the angle in that air is angle I. So when I say refractive index times sine I, the answer I'm going to get will be the same when I multiply the sine of this angle with its refractive index, N2 times sine R. So this is the simplest. You can always understand this law. Just multiply sine of that angle with its refractive index, equate it to the sine of the other angle multiplied with the refractive index in that of that medium. It will be simple. You'll have understood, or you'll be able to solve issues to do with refraction. So for maybe to highlight for you, refractive index for air, we always approximate it to be around 1, where it may be like 0.99 something, it may be 0.9 something, or 1.0 something. But then that of glass, we approximate it to be like 1.5, For water, we approximate it to be around 1.33. So these are some of the common media that we use in refraction. After we have now known the Snell's law and the equation, we can look at an example on refractive index, which says if the angle of incidence in oil is 52 degrees, find the angle of refraction in glass for a ray of light traveling from oil to glass. And they've gone ahead to give us the refractive index of oil to be 1.2 and the refractive index of glass to be 1.5. Refractive index, we use N to represent refractive index, 1.52 for glass. So how can we do that? Using Snell's law. Maybe it is always important we can first illustrate. We illustrate it like this. We are saying a ray was coming, the ray was incident on oil at 52. This is oil, and it then goes to glass at an angle R, which is the angle of refraction, which we don't know. Then, but we know the refractive index of oil was given as 1.2 and that of glass was given as 1.52. We can use now our formula and we see how does it look like. Remember, we said we can use refractive index N1 times sin I, N2 times sin R. N1 is what? It is oil. And the angle in oil, do we know it? Yes, 52. So if we substitute in, refractive index of oil was given as 1.2, the angle there is 56. Refractive index of glass is 1.52, the angle there, we don't know it. So it's what we are looking for. So if you get your calculator, remember when you're doing this calculation, make sure your calculator is in deg or degrees. It should be in deg. If it is in rad or grad, make sure you remove it and you put it back in deg, because we want these angles are in degrees. So we go ahead, you know, when you put this on a calculator, it should be able to give you 0.9456. The right hand side has remained the same. We go on to divide both sides by 1.52, which becomes this. And for us to get R, it means we have to take sine arc or arcsine or sine inverse, which will be this. And finally our R will become out as 38.47, meaning the angle of refraction in the glass will be 38.47. Now refraction has some effects in real life. And what are some of those effects? If you have ever stood near a swimming pool or a pond, you must have realized that it appears to be shallow. When you stand on it, it looks like the bottom is very near, when in actual sense it is very deep. Now this is one effect of refraction. What exactly happens? The rays that are supposed to come from the bottom, when they reach the surface, because they are moving from water going to air, I want you to see these rays. These are the incident rays coming from the bottom. Now when they reach the surface, they are coming from water entering air, meaning will they bend towards or away from the normal? They will bend away from the normal, you're correct, because they are moving from more dense going to less dense. So they will move away. If we construct imaginary normal here, these two rays will be bending away from the normal. Now when they bend away from the normal, they will enter your eye, and your eye does not see the bend, for it tends to see in a straight line. It will create the image where these rays are going to meet here, meaning that is where it will see as if that is the bottom. Now for you, your eye will be seeing that the bottom of the swimming pool is here, when in actual sense it is here. And before you know it, you jump in that, then you'll have to be asking for help, because you will start swallowing some cups of water. So don't ever play near a swimming pool thinking it is shallow, yet it is very deep. It is due to refraction. Another scenario is if you placed, like, let's say, a coin or a mark in a glass or at the bottom of a glass, and you put there water, it will appear as if the bottom is very near, or the coin will appear as if it is near. Same issue. Rays from the bottom, they reach. When they are emerging out of the water, they bend away from the normal. So for you who is observing, who is seeing the rays, you'll see as if they are meeting here, yet they are supposed to be meeting there down. So as a result, it appears like the coin is raised. Another issue is if you've ever placed a pen or a stick in water or in a cup, it will appear as if it is bent, as if it is broken, when in actual sense it is straight. Now why? Simply because, same thing, the stick is here straight, see the gray part, that is where the stick is supposed to be. Now the rays from the bottom, they are coming, as they are moving out, they are bending of course away. For you as an observer, you will see as if the rays are in a straight line. So they will be combining, or they'll be meeting at this point, because you're seeing them in a straight line. Now that point where they are meeting, remember they were coming from the bottom. That is, your eye will be seeing as if the bottom of the stick is here, and yet the stick has to continue, it has to join itself, so it will be appearing as if it is bent, when in actual sense it is straight. Another scenario is of and many other applications. Now let's look at total internal reflection. Total internal reflection, what happens is, if you increase the angle of incidence, the angle of refraction will also increase. Now the point will reach when the angle of refraction will no longer increase, the ray will just graze the boundary, or it will no longer be refracted, it will just bounce back. And we know the moment it bounces back, that is now reflection. Now that is what we call total internal reflection. And when this happens, the angle between the incident ray and the normal, which we call the angle of incidence, this time it is given the name critical angle. This time it is given the name the critical angle. And this can only be achieved if this ray is moving from a less dense to a more dense medium. I want us to first look at this situation. We study it as we see what exactly happens under total internal reflection. So let's look at this issue where we have our two media, and we want to see how refraction takes place. Let's first have a protractor so that we can see the angles very well. The protractor is sitting exactly at the boundary, and this line is acting as the normal. So we first see that if we put medium 1 to be air, and we put medium 2 to be water, you can see air is gray, then water is blue. So we know air is less dense than water, so we expect if we put our ray, let this be our ray, we put it at 20 degrees, the angle from here to here is 20. So if we allow that light to go through, we expect an angle this side which is less than 20, because we know it should be bending towards the normal. Sorry, it did not put it at the center, let it be here. So we can see now that our ray is here. It was if I put it at 20, and we see what do we have. If we put it at 20, you can see that the angle we are having here between the normal and the refracted ray is around 15, so which is less than, which confirms to us that when it is moving from a less dense to a more dense, it bends towards the normal. Whereas now, what if we make medium 1 to be water and medium 2 to be air? We expect the ray to bend away from the normal. So let us go. We see now the angle of incidence is 20. We want to see what will be the angle of refraction. So the angle of refraction, you can see here incidence was at 20, and now the refracted angle is beyond 20, it is around 26. So which shows you that when it is moving from a more dense to a less dense, it will bend away from the normal. But that's not what I wanted us to see. I wanted us to see total internal reflection. So we said for total internal reflection, the ray must be moving from a more dense going to a less dense. So I can change and use another medium. Let's say oil. Let me use oil to be our more dense, and it is entering air. Now, if we start with the angle when it is, let's say 20, we can go and see. We see now the angle of refraction is around 30. Let's increase the angle of incidence to, let's say 30. And we see what do we have. When we got 30, we see the angle of refraction is almost remaining 30. We go to around 40. We see what do we get. When we got 40, we see the angle of refraction. Oh, sorry, is there something that it is not doing well? Let me see. It is not giving the result that I wanted. Okay, yeah, it has now shown you that. At 35, what was the angle of the angle of refraction was around 60. At 45, the angle of refraction, it is now totally internally reflected. So we see that at around 40, it was when the angle of incidence was 40, it was coming out as 40, it was going through and deviated. But when we go to 45, we see that the ray is no longer being refracted, it is totally internally reflected. Why is it called internal? Because it is being reflected within the same medium where it was coming from. So that shows you that this is total internal reflection, and this angle now, at this point where it is totally internally reflected, like we've seen, it was around between 40 and 45. I don't have enough time to check exactly the angle, but that angle is the one that will be named the critical angle. So that is how total internal reflection occurs, or how it happens. Now that we have finished looking at how total internal reflection occurs, let's look at some applications. Where is total internal reflection useful? We have optical fiber or communication cables. Have you ever seen wires on trees which are not electricity wires? Those are called optical wires, optical fibers, or communication cables. Now inside they are hollow, like you see this pipe here. What they do is they keep reflecting the signal that is being sent. Let's say you're making a phone call, you're sending a message, you're sending something. That call is running through this wire at a very high speed, you know, the speed of light, but it is being totally internally reflected. So we see that is one application where total internal reflection is being used. Next is like submarines, those which move underwater. They use periscopes. You may have made a periscope even in your senior one, where you made using plane mirrors, but here they use prisms. And you must have looked at advantages of using prisms other than plane mirrors. Prisms, they totally internally reflect, meaning you don't lose any light, the object remains clear. So they also apply, you see a ray enters the prism, it gets totally internally reflected, it meets another prism, gets totally internally reflected. Then another ray from the bottom of the object gets totally internally reflected, then totally internally reflected, and it enters the eye of the observer. So the object remains upright and very clear. So that is where else the total internal reflection is applied. We also have formation of a mirage. If you've ever moved along a hot road during a hot day, you should be able to see, sometimes when you look ahead, you see as if there is a pool of water, as if there is a water or a lake on the road. Now that is called a mirage or a mirage. It is an impression. It is actually what you're seeing the sky. Now what happens during a hot day? You know the earth is very hot, meaning the air above the earth will be hot, and we know when an object is hot, it becomes less dense. It expands and becomes less dense. So as a ray comes from the air, from the sun, it is coming towards the ground. The air above the ground is hot and less dense, so it will be bending away from the normal until a point reaches when it is totally internally reflected. Now when it is totally internally reflected within that air, it will enter your eye, and your eye will see as if that ray is coming from down. Remember we said the eye sees in a straight line. So the eye will be receiving a ray from the sky, but it will see as if the ray is coming from the ground. That's why you will see as if there is a water on the ground. Another application is sky radio waves. Radios which don't use satellites, they as well transmit their signals using these waves. We know up in the sky there is no atmosphere. There is no atmosphere, so as a result the air is very less dense there. So as a signal that comes from a station A, it travels in the atmosphere, it starts being refracted until a point reaches where it is totally internally reflected, and it will come back to earth. Now instead of coming back to where it was sent, it will go to another area, meaning the person there who is having a radio will receive that signal using the antenna of the radio, and that person will be able to receive the signals or even the news or whatever he wants to listen to. Those are some of the applications of total internal reflection, and that is about total internal reflection. You'll be doing more research in the books to add on your notes, but let's look at now refraction in prisms. We've seen how we can refract in water, air, oil, glass block, any. So now we want to talk about the prisms. Now, like other surfaces, the prism is also there to reflect. The only issue with it, it has two sides. There is this side, it is triangular in nature. So there is side AB and then side AC. So a ray that enters through side AB, remember if it is coming from air, it will be bending towards the normal. If we construct a normal on that line, on that side AB, then the ray will be bending towards the normal. That is why you see when it is entering here, it was entering from air, it is bending towards the normal. But as it bends, it continues running, it meets another surface. So now at that boundary, it is moving out from glass going to air, meaning now it is moving from more dense to less dense, meaning it will bend away from the normal. So that's how the prism refracts light. It always tends to bend it towards the base of that prism. The reason is simple, because as the ray enters, it's bending towards the normal. As it meets this surface, it will be bending away from the normal, since it is moving from more dense to less dense. So this is the incident ray, this is the refracted ray, this is what we call the emergent ray, the ray which is emerging out of the prism. Now this issue here comes with challenges. A prism will always create a rainbow, and this is where now we want to start looking at it. It brings us to the next part, or in our next lesson, where we shall be looking at dispersion of white light and colors. I thank you for being good students and for attending this lesson. Have yourselves a blessed day.